These are the notes for Unit 8, Day 9, and we are looking at continuing to develop our strategies and finding the volume of three-dimensional shapes. And so today we're going to talk about something called the disk method. So our essential question then is, how can we adapt our knowledge of known cross-sections so that we can calculate volume using disks? And so this is a problem that might look familiar to you. We have this XY plane. The red axis is the X, green axis is the Y, right? And we have this parabola bounded by the axis and the parabola. And this footprint, this space, then we have a quarter circle, a cross section of a quarter circle. And we want to know what the volume of this shape is. And so this is a known cross-section problem, right? We take our cross-sections perpendicular to the x-axis, quarter circles, and so if we were treating this like a constant cross-section problem, we'd have an area function, which is pi r squared divided by 4, right? Because it's a quarter circle, where our radius goes from the x-axis to that parabolic function. And so that means our radius is the function value of listed up here. So when we simplify that, we can, the square and the square root kind of cancel each other out there, and then we can integrate that area function. And we're stacking these quarter circles from x equals 0 to x equals 4, right? Those become the limits. And then we can go ahead and integrate that, right? This is easy enough to integrate by hand. And then we can plug in the 4. Don't need to plug in the 0 because that will just give us a value of 0. So we plug in the 4 and we can find our area for that known cross-section, and it's 2 pi. And so what we're going to do is we're going to extend this to our new strategy of using disks. So the idea here then is that instead of dealing with this quarter cross-section, what if we were able to continue to rotate that parabola, right? There's that quarter cross-section, and that parabolic function in the xy plane, I've got it rotated up here to the z plane, that's this vertical plane. And so I'm going to extend that rotation, and I'm going to take it all the way out here, which means I've basically doubled its volume, right? Because I've added another quarter circle to the cross section, and now I'm taking it down underneath into the negative z territory, and now I've got 3/4 of a circle, and now I've got a complete circle. And so what we have basically is 4 of those known cross sections kind of all glued together in the center. And when we do that, then this solid becomes a cross section that is a full circle or a disk. And so we can now, we can really approach this as using a known cross section, where the known cross section is a whole circle, which is just a pi r squared instead of a quarter circle. And so but let's kind of compare and contrast then these different methods. Solids of known cross section, which is what we just got done doing, we build the volume on its base in the xy plane. And those cross sections were stacked right from 0 to 4. And that cross section can be a variety of shapes. I could have done a square or a triangle or something like that. When we talk about solids of revolutions, the volume is built by revolving about an axis. So that revolution, where we could equate it by, in that particular problem, by having 4 quarter circles stuck together, we can really, instead of using a known cross section, we can just say, well, I've rotated it all the way around that axis. What was that? The x-axis, and I've completed that rotation, so I have a cross section now of a complete circle. The cross sections are still stacked. Those circles were still going from 0 to 4, but they are in fact circles. So the solids by revolution, because of the virtue of revolving about an axis, we are forcing that shape to be circular, and so we don't have the variety of shapes. And so when we're talking about this expression here for known cross sections, we're used to this, right? We're going from 0 to 4. We have our area function. We integrate it. Well, now our area function is the area equation for a circle. So this changes the volume expression a little bit, and instead of having a generic area function for a variety of shapes, we can just put in the area function for a circle, which is pi r squared. And that radius of revolution often is the function itself that's given in the problem. So when we take a look at this from a revolution standpoint, so let's look at the stem now and see how it's changed. Revolutions, using a revolution is kind of a better idea. It beats multiple known cross sections, right? We know that this is 4 quarter circle cross sections or 2 half circle cross sections if we wanted to deal with it as a known cross section. But a revolution is just a more efficient way of dealing with the calculation of the volume. So the stem kind of goes like this. It says, let a region bounded by the x-axis, the y-axis, and the parabolic function y equals the square root of 4 minus x be revolved around the x-axis. I keep calling this a parabolic function because it's a sideways parabola, right? It's y squared equals 4 minus x. It's a square root function, but it's just a sideways parabola. It says find the volume of the resulting solid. So the first thing we want to do here is we want to graph this. So I usually graph these things point by point. So when x is equal to 0, so again the red axis is x. When x is equal to 0, y is the square root of 4, which is 2. So it's at that point right there. When x is equal to, let's see, what would be a convenient number to choose. When x is equal to 4, then 4 minus 4 is 0, so y is 0, so I get that other intercept point there. And if I put 3 here, then x is equal to 3, then this becomes 1, square root of 1 is 1. So we know we have the smooth curve that in the xy plane that looks, I guess I extended it over here to the negative values, right? Because square root, we get a positive and a negative y. We've got that sort of parabolic cross section, so to speak. And so, here's that sideways parabola I was mentioning just a moment ago. So we are talking about just that first quadrant right there, right? That's this positive root. And so we're literally taking this line and we're spinning it up into the positive z region and then down into the negative z region. And so we're getting that cross section, this pink cross section that is pi r squared. And where the radius is, because we're revolving about the x-axis, the radius is measured from that axis of rotation out to the function. So that ends up being pi times the function squared. And then as we simplify this, the root and the square go away. And so this is our area function for the revolution. And so there's our pi r squared from 0 to 4, because we're going to stack these pink circles starting at x equals 0 and all the way out to x equals 4. And go ahead and integrate that. That's easy enough to integrate by hand. Substitute in 4 and substitute in 0. Substituting in 0 really isn't necessary. And as we simplify that, we get 8 pi. So notice our answer for the revolution, because it is 4 quarter circles, it's 4 times the volume, right? And so this is, for revolutions, it's really a more efficient process than to try to break this up into known cross sections. So let's take a look at another one. So here's another one where we have a cubic, and it's graphed in the xy plane here, and we're going to revolve it about the x-axis. So we're going to go about this red axis again, and it's going to swing up into the positive z, down into the negative z, and it's going to have this flat disk here. So let's take a look at that. So here's that function, that cubic function, and we are going to now rotate that cubic function all the way around the x-axis. So we rotate it up into the positive z and down into the negative z. And you can see that pink disk that's created. That's the cross-section of the shape. And we get this kind of interesting looking solid that's got a really big, wide circular base and then comes to a really sharp point at x equals 2 here. And so looking at setting up that, that cross-section then in the xy plane, when x is 0, 2 cubed is 8, divided by 2 is 4, so put that point right there. When x is 2, then y is 0, I've got that point right there. When x is, I think I have 1, yep, when x is 1, then 2 minus 1 is 1, cubed times a half is a half. So I have this smooth curve here. And since I'm going about the x-axis, my radius is then from the x-axis out to that function. There's my radius, which means my radius is just the function value. And so I put, because I know I'm going to get circular cross-sections, we know that the area function is just pi r squared. So I'm going to put the radius, I'm going to put the function in for the radius. I'm going to do a little simplifying here. And that's my area function. So I know that these pink circular cross-sections are going to be stacked from 0 to 2. So that's going to become my limits of integration. And this is what I'm integrating. And we can do a u sub here. This is, technically one that we really could ask you to do without a calculator. So if we substitute the stuff inside the brackets as u, and then we take the derivative, that's minus 1. Then dx is du over negative 1. And so this becomes u to the 6th power times du over negative 1. And then when I integrate that, here's the negative 1, u to the 6 becomes u to the 7 over 7. That was probably a pretty big step to make. I probably should have had some steps in between there. And then notice my change in units. And so that change in units comes from the fact that I'm doing a substitution on the upper and lower bound. So when x is 0, and I put 0 in here, u is 2. So that's how the 2 got down here. And when x is 2, I put the 2 up here. 2 minus 2 is 0, so the 0 goes up here. And I'm going to stick with that. Since they want a numeric answer, I'm not going to go back to x. So I put in my 0, and then I put in my 7. Minus a negative becomes positive. That's how this whole thing is 0. Minus a negative becomes positive. That's how we get a positive volume. And we get 2 to the 7th over 28, and we get a pi in the numerator. So that looks like this. And this is what 2 to the 7th is. And you can reduce that, but that's not necessary to reduce it. But if you want to reduce it, you're dividing out 4 because we have a 4 up here. This becomes 2 to the 5th if we take out a factor of 4. So it's definitely doable by hand. This falls into the category of maybe potentially using Math 9 on your calculator too. It's a tough one to kind of figure out where they might put something like this. If you want to see, oh, here we go. I think it was just out of sequence. Here's the rest of the u sub. So u is here, right? U to the 6th. Dx is this. We can, we can then probably at least jump from here to here pretty easily. Okay, so let's take a look at, if you notice, let's go back here, right? This function that we were dealing with here, rotating it about the x-axis, we're actually going to look at the same function, and now we're going to rotate it about the y-axis. So now our radius, because our radius always goes from the axis of rotation out to the function, our radius is now going in this direction, parallel to the x-axis. So our radius now is, this will be an interesting conversation here. as to what we have to do to get this value to put into our integration. So I call this kind of the witch's hat. It's kind of what it looks like. So same function, and let's take this one, and as we take this about the y-axis here, we're going up into the positive z's, and then back down into the negative z's. So we're getting a similar sort of shape, right? It's got a big circular base, just like the last shape did, and it comes to a point at the top there, but it's a taller volume with not as big of a base. And then here's that circular disk. Okay, so I'm just going to scamper through the graphing here, right? The graphing of the function in the plane is the same as the previous example. We've got 4 here. When x is 0, we've got 2 here. We're down at, when x is 2, we're down at 0, and then when x is 1, we're here at a half, right? These are counting by a half, so along the y-axis here. And so let's talk about this r. So in terms of the x-axis is red, the y-axis is green still. So in terms of the xy plane, this r is really the x-coordinate. So that being the case, we have to solve this for x, because that's what r is. And so rearranging this for x, then we got to multiply by 2. We got to take the x cubed over here and the 2y over there. And then, oops, I'm sorry, we got cube root both sides, then take the x over here and the y over there. So it requires a little bit of algebra to solve for x, but we get this. So now we can substitute that into our function. Notice this is, because we're revolving about the y-axis, this is a dy problem. In other words, these disks have a thickness here, right? And this thickness is vertical. Vertical is probably a poor choice in words, but this thickness is along the y-axis. So it's this thickness represents the differential. So this happens to be a dy. So I call these things dy problems when we revolve around the y-axis. So integrating that area function, and so we're stacking this disk from here all the way up to here, so from 0 to 4. So these measurements are along the y-axis because it's a dy problem. We're integrating this with respect to y, which means we're just doing the power rule with respect to y. But this definitely falls into the use your calculator category. So if we do a math 9 on that, and then we can put in 0 and 4, and then we can put in that expression of, now whether or not you put the pi in now is up to you. I'll put it in. Pi times the quantity 2 minus the cube. We have a cubed root, I believe. I think it's under math. There it is. So we do have a cubed root. It's right there. Otherwise, you could do a 1/3 power. And then 2, and our variable will always be x, even though it's written as y on the paper, on the solution that you submit. And then we have to put a closed brackets, and we have to square that. And then we have to come over here and put our differential variable. So I've got the pi in there. I've got my final answer. So it's going to think for a little bit. There's my final answer. Now, if we go to the screen here, oh, we do get the final answer. Okay. Sometimes, let's just back up here. Sometimes, especially in the multiple choice questions, sometimes they leave it in terms of pi. So in other words, they get rid of this, and your answer will be something pi. So when we do that, 1.5999, you might encounter an answer of 1.6 pi on a multiple choice question. So just know that that's an option that might happen on a multiple choice. But it would be a calculator multiple choice either way. Okay, so let's take a look at this function. So now we're going to put in a little bit of trig, right? We've got y equals sine of x, and we're only going from the x-axis to pi over 2. So if you think about the unit circle, right? From 0 to pi over 2 is that first quadrant of the unit circle, so to speak. We know that when x is 0, sine is 0. When x is pi over 2, sine is 1. And then we have this, this is your sine curve, right? So looking at this, you can see in light gray, here's our sine function as we would graph it. Here's the first quadrant, or here's from 0 to pi over 2. So we're going to revolve that. And notice we're revolving that about a line that's not an axis. Right? We're revolving it about this line right here. And that's pi over 2. So our R becomes a little more complicated. So we still have a circular cross-section though. It's just about the line pi over 2. And you notice the thickness is still dy. And so looking at that, we get this kind of dome-shaped looking thing. So as we graph this, there's our graph in the first quadrant. We talked about the first and the last point here. These 2 points here are like pi over 4 and pi over 6. Yeah, pi over 6. Yeah, because it's half. So I got pi over 4, which is root 2 over 2, and then pi over 6, which is a half. Just to help me get some curvature. You don't really have to graph those points. A sketch would be fine. And this is our radius of revolution, right? We're revolving about this line, and this line is this, x equals pi over 2. And so we have to measure from that point of revolution to the function. That's defining our radius. And so this gets a little complicated because this is being rotated rotated about a line parallel to an axis. Does that make sense? It's parallel to the y-axis. And so in terms of the Cartesian plane, right, the xy plane, again, our x-axis is the red and our y-axis is the green. Excuse me. And so in terms of that Cartesian coordinate system, if I looked at this point here, this point would have the coordinates x comma y, where x is measured, where that's measured from the origin, right? We go out x and up y to get to that point, and neither the x nor the y is the radius of revolution. So it has to be built from those Cartesian coordinates. So it gets a little complicated, and so we're going to do that now. So we know that we still have circular cross-sections, so our area function is pi r squared. That's by default. When we revolve things, it's by default that we have an area function that's a circle. Let's talk about that radius. So if this point here is a distance of x away from the origin, and this point over here on the other end of my radius is a distance of pi over 2, then my radius is pi over 2 minus x. It's the part that is left over after we cut off this x coordinate, that x distance. So that's your radius of revolution, and we're gonna, and then I kind of mentioned that the disk was a dy, so we have to solve then and get this in terms of y. So when we solve that, it's sine inverse of y, and so that gives our area function, excuse me, lost my train of thought there, as pi r squared, which is pi times the quantity pi over 2 minus sine inverse of y. Right? This is pi over 2 minus x. So this is pi times radius squared. And as you might guess, this is going to be a calculator question as well. So we are stacking these circular disks. We're starting here and we're ending up here. So we're going from 0 to 1 on the y-axis. Here's our pi r squared dy. And when we put that into the calculator, let's go ahead and do that. We're going to do a math 9 from 0 to 1. And we are going to, I gotta move this off to the side here. we have to square something, so I need some brackets. So bracket and pi divided by 2 minus inverse sine. So second sine variable, got to close my trig, got to close my radius, and I got to square it. Oops, that's not squared. Got to square it. And then I got to put my dx. There, there's my variable. So notice what I have is lacking the pi. Okay, and honestly, it's lacking the pi because I just forgot to put it in. I'm going to hit enter anyway. So it's 1.1416, let's call it, times pi. Okay, so let's see what answer I have here. I've got this. Okay, so if I take this and multiply it times pi, because I left the pi out of the integrand, right? It should have been out here in the front. Then I get my 3.586 answer. So that's the volume of that solid. Okay, let's take a look at one more. And again, let's go back to example 4. Right, this is a revolution of a function about a line parallel to an axis. And so when we are parallel to an axis, we have a more complicated r. It's offset from the x-axis. And likewise, in example 5, we're going parallel to the x-axis. So our radius is going to be this more complicated offset expression from the x-axis. So now we have this quadratic function. It's x squared plus 4x plus 4. So this is factorable, and it's irrelevant of the fact that it's factorable. But it's x plus 2 squared. But that helps you see that how this is graphed, right? X plus 2 squared is shifted left 2, and it's a repeated root, so it's tangent at the x-axis. So that's how I would quickly graph that. So looking at revolving this about the line y equals 4, right? So the line y equals 4 then allows this parabola to come back to the y-axis. And as we spin this up into the, I think we go up into the positive z, we might not. We might go down first, yeah, there we go. So we go down into the negative z, and then we go up into the positive z, and we create this shape that kind of looks like an M&M, or maybe a Skittle, right? Something like that. I always seem to have this reference to food, but so we have that nice solid M&M looking shape. Okay, so coming back to this then, we can graph this point by point, right? When x is 0, y is 4, that's that point right there. When x is negative 2, y is 0, that's hard to see. But, and then when x is negative 4, y is 4 again, because this would be 16 and minus 16. And then maybe 1 and 3 might be helpful. You know, it wouldn't be hard to crank out when x is negative 1. I said 1, I meant negative 1. When x is negative 1, then y is 1, and we can get the symmetry. We wouldn't really need to calculate the negative 3. So there is our sketch, and then we need to identify the radius. So that radius goes again from the axis of revolution to the function. So the radius in this case happens to be going quote unquote down. That's irrelevant though, because we're going to square it. All right, so we know our area function's pi r squared. We always start out by saying that. And now we need this radius function. So we know the radius then, with the same argument about being this point on the function is over x and up y, then this radius length becomes 4 minus y, right? We don't have this part to the radius because it's outside the function and the axis of revolution. So this radius goes from 4 down to the function y, so it's 4 minus y. And so the cross sections are for this are perpendicular to that axis of revolution. So this is a dx problem, so we're going to take this function and substitute it in for y, so we can get it in terms of x. And now we have a radius. I would simplify this because that looks pretty nasty, right? So we distribute the minus sign, and when we do that, we get 4 minus 4. Those go away. So our radius is really minus x squared minus 4x. That's a little easier to deal with. So our area function then is this squared times pi. So we have that. And then, so we can set up our volume. Now we're gonna, this is interesting, right? These limits of integration, because we always stack, when we're making solids, we either stack from left to right or bottom to top, right? So if we're stacking from left to right, then that's -4 to 0. That's how we get those upper and lower bounds. And then here's our area function. And so I just did a quick math 9, and that gets us 107.233. I think it's probably easy enough to do a math 9 on your own for that one. Okay, so when we get back into the classroom, we'll go over the takeaways, and we'll start working on developing those area functions for full circles now, since we're revolving.